In this lesson, we will discuss the various methods used for trimming an aircraft in roll, pitch and yaw. An aeroplane is said to be in trim when it maintains its attitude and speed without the pilot having to apply any load to the cockpit controls. If the pilot does need to move a control surface to maintain the balance of the aircraft, he will need to apply a force to the cockpit control to hold the surface in its deflected position. This is commonly known as stick force, irrespective of which control is being operated. This force may be reduced to zero, thereby reducing pilot fatigue, by operation of the trim controls. The aircraft will need to be trimmed in pitch as a result of changes of speed, changes of power, or varying centre of gravity positions. Trimming in yaw will be needed on a multi-engine aircraft if there is asymmetric power, or on a single-engine aircraft as a result of changes in propeller torque. Trimming in roll is less likely to be needed, but could be required if there is asymmetric power, or if there is a lateral displacement of the centre of gravity. There are 5 methods commonly employed to trim the aircraft. In this lesson, 4 of them will be explained. The 5th, adjustment of the artificial feel unit, is covered in the lesson on powered flying controls. The 4 we are going to discuss are the trimming tab, the variable incidence tailplane, the spring bias system, and centre of gravity adjustment. The trimming tab is a small adjustable surface set into the trailing edge of a main control surface. Its deflection is controlled by a trim wheel or switch in the cockpit, usually arranged to operate in an instinctive sense. This allows the aircraft to be maintained in trim throughout its entire operating envelope. Here, we will describe the operation of an adjustable trim tab fitted to the elevator control. However, the explanation remains good for a tab fitted in either the rudder or aileron systems. If the pilot were to pitch the aircraft nose up, then to continue to fly at that new attitude, a force must be continually applied to the controls by the pilot to balance the control surface hinge moment. The tab is moved in the opposite direction to the control surface to apply an increasing opposing hinge moment at the control surface until its hinge moment balances the control surface hinge moment. You will recall from the aerodynamics lessons that the hinge moment is equal to the aerodynamic force, multiplied by its distance from the hinge line. In this example, the control surface hinge moment is distance A multiplied by force F2. Although the tab is small in relation to the control surface, and its aerodynamic force F1 is similarly small, its distance B from the control surface hinge line is much greater than that of the control surface force distance A, so it is able to balance the control surface hinge moment. The aircraft will be in trim when F2 multiplied by distance A equals F1 multiplied by distance B. There are a number of disadvantages to using an adjustable tab type control to achieve trim. These are a slight reduction in control effectiveness due to the tab force being in opposition to the main flying control surface, and an increase in drag due to the deflection of the tab. Fixed trim tabs are not adjustable in flight, but can be adjusted on the ground to correct a permanent out-of-trim condition. They are usually found on ailerons. They operate in the same manner as the adjustable tabs. Fixed tabs are used on simple low-performance aircraft. They achieve an in-trim condition at a particular speed, normally the aircraft's cruising speed. Their correct position is usually found by a process of trial and error. A variable incidence trimming tailplane or stabilizer does not have the disadvantages of the adjustable elevator trim tab. Plus, it has the ability to trim for larger changes in speed and centre of gravity position. The system is controlled from the cockpit and can be either manual or power operated. The operating power may be electrical or hydraulic. The Boeing 737 stabilizer trim, for instance, is electrically powered, whereas the one on the 747 is hydraulically operated. In a power-operated system, tailplane movement can be controlled either manually or electrically. Electrical control is by trim switches, which operate in pairs. These are usually found on the control column or yoke. There may also be a pair of manual control levers mounted on the centre console. Either both switches or both levers must be moved simultaneously in order to trim the aircraft. And as a pilot, this is how you always use them. Consider them to be a single switch or lever. The reason why there are two switches and two levers is to prevent the short-circuiting of a single switch or the jamming of a single lever, causing an undemanded trim operation or trim runaway. An example of the operation of a variable incidence trimming tailplane to achieve trim after a change of attitude is shown in this graphic. The elevator is deflected to change the pitch attitude. The angle of incidence of the tailplane is now altered by the pilot to achieve trim. The amount of trim required will depend on the centre of gravity position. In order to ensure that the aircraft will be trimmed in pitch on takeoff, recommended takeoff stabilizer settings based on aircraft weight and centre of gravity position will be given in the aircraft flight manual. The acceptable takeoff range for the stabilizer setting will normally be shown on the stabilizer trim indicator by a green band. The stabilizer trim takeoff setting is one of the parameters monitored by the takeoff configuration warning system. This is a system that warns the crew if a takeoff is attempted with the critical system not correctly configured. The warning normally takes the form of an intermittent horn. The horn will sound if the aircraft is on the ground and the thrust levers are advanced for takeoff, and the stabilizer trim is not in the takeoff range, or the trailing edge flaps are not in the takeoff position, or the leading edge devices are not in their takeoff positions, or the speed brake lever is not in the down position. This list does vary slightly between aircraft types. Some aircraft systems also monitor other items, such as the parking brake, external doors, body gear steering, or even control locks. In the spring bias type of trim system, an adjustable spring is used to reduce the stick force. No tabs are required, so the spring system does not have the disadvantages associated with tabs. The spring bias system differs from the other systems discussed so far, in that the device is connected not to the flying control surface, but to the pilot's control. The trim control biases springs which apply a force to the control linkage to oppose the stick force. The graphic shown here demonstrates the use of spring bias in a rudder control system. The pilot operates the rudder pedals to move the rudder. He will now have to maintain a force on the pedals to oppose the rudder hinge moment. By rotating the rudder trim knob, the angle of the arm between the springs is changed, thus biasing the spring pressures until they are equal to the hinge moment. The pilot can now remove his feet and the rudder will remain in position. We will now look at longitudinal trim by centre of gravity or C of G adjustment. While the variable incidence tailplane produces a drag reduction over a trimming tab, the minimum drag will be produced if the tailplane can be made aerodynamically neutral. This can be achieved by moving the aircraft's centre of gravity as close as possible to the wing's centre of pressure. On long-haul aircraft, this can produce a significant fuel saving. The method usually employed to move the centre of gravity is by transferring fuel between tanks located at the nose and/or tail of the aircraft. The Airbus A340, for instance, has a fuel tank in the tail specifically for this purpose. Fuel is automatically transferred between this and the wing tanks to maintain the C of G as close to the centre of pressure as possible. In the graphic shown here, the C of G is forward of the centre of pressure. Fuel is pumped from the forward to the aft tank, moving the C of G aft until it reaches the centre of pressure, when the pumping stops. On most large turbojet aircraft, the wing centre of pressure moves rearward as the aircraft approaches high subsonic speed, and this produces large nose-down pitching moments, known as tuck-under or mac-tuck. It is essential that the aircraft is fitted with an automatic system to correct this change in pitch attitude. Such a system is known as Mach trim, and is designed so that it will operate whether or not the autopilot, or some other method of automatic flight control, is engaged. The system senses speed increases above a datum Mach number, approximately Mach 0.65, but this does vary with aircraft type, and through a servo system produces the appropriate movement of the horizontal stabilizer, or a fuel transfer to maintain the trim flight position. The trim controls are usually on the centre pedestal. In this typical setup, there is a large wheel for pitch trim, a smaller wheel for rudder trim, and a guarded switch for aileron trim. You will note that the wheels and switch all operate in the plane in which they trim. If the pitch trim can be controlled electrically, then there will also be control switches on the outboard arm of each yoke or control wheel. That is the end of the lesson on trimming. These are the main points that you need to remember. The trimming tab is a small adjustable surface set into the trailing edge of a main control surface. It allows the aircraft to be maintained in trim throughout its entire operating envelope, reducing the stick holding force to 0. Fixed trimming tabs are not adjustable in flight. They can only be adjusted on the ground. The disadvantages of trimming tabs are a slight reduction in control effectiveness due to the tab force being in opposition to the main control flying surface, and an increase in drag due to the deflection of the tab. A variable incidence trimming tailplane does not have the disadvantages of the elevator trim tab. Plus it has the ability to trim for larger changes in speed and centre of gravity position. It is controlled by 2 switches or levers to reduce the possibility of trim runaway. Longitudinal trim by centre of gravity adjustment is used to maintain the centre of gravity close to the wing centre of pressure. It is normally achieved by transferring fuel between forward and aft tanks. Mag trim is an automatic system used to counteract Mach tuck at high subsonic Mach numbers.